All right, hey again, organic chemistry. So I'm jumping to the second part of our notes. We're actually going to skip page 13 and look at the bottom of page 14. I'm going to begin talking to us about empirical and molecular formulas and then how I could calculate them. So just to remind you, an empirical formula has the elements in the compound in the simplest ratio. So CH4 and CO2, I cannot divide those any further, but something like C2H4, I could divide both those numbers by 2 and I get CH2. That's an empirical formula, whereas these bigger numbers, that's a molecular formula. There's a specific way in which we could calculate an empirical formula, and it's by using percent composition data. There will be times in the beginning of our semester where I will give you a percent composition of each element in a compound, and you're going to have to convert those percentages and eventually be able to get the formula of the compound. So there are a couple of steps. If I say a compound was analyzed and found to contain 25.9% nitrogen and 74.1% oxygen, and I ask you for the empirical formula, these are the steps that you follow. And this is a bit of throwback from intro chemistry, beginning chemistry, or if not, I'm going to just remind you. Assume that we have 100 grams of sample and convert the percentages to mass and grams. So this percentage automatically becomes grams. So 25.9% becomes 25.9 grams of nitrogen. 74.1% oxygen becomes 74.1 grams oxygen. Then the next step, which is step 2, is convert the mass of each element to moles using the molar mass from the periodic table. If you look on a periodic table, you'll see, especially the ones that we work with, there is like a symbol, and at the bottom will be the mass, and then you have the atomic number. So on the bottom is a mass, that's its molar mass. Basically, if I have a grams and I divide by the molar mass, I get moles. So nitrogen, if I look on the periodic table, its molar mass is 14. The grams that were given to me was 25.9. If I divide these two, I get 1.85. Same thing with oxygen. Its molar mass is 16. If I divide these two, I get 4.63. Then step 3 says divide each mole by the smallest number of moles calculated. So between 1.85 and 4.63, I divide by the smallest moles, which is 1.85. I'm dividing both of these by 1.85, and I'm going to get a new number, which is the relative number of atoms in the compound. So if I divide 1.85 by 1.85, I get 1n. If I divide 4.63 divided by 1.85, because it's the smallest moles, I get 3. And that corresponds to oxygen, so it's 3O. 1N3O, there's our empirical formula. It's NO3. It's the simplest ratio, and you get that from percent composition data. And then to further talk more about molecular formulas, they are a whole unit amount larger than the empirical formula. So an empirical formula for CH has a molar mass of 13. The molecular formula of something like ethine is 2 times the molar mass of the empirical formula. So the empirical formula's molar mass is 13 because carbon is 12, hydrogen is 1. Ethine is 2 carbons, 2 hydrogens, that's 26. That's twice the amount. Benzene, also, empirical formula of benzene, if I divide them both by 6, I get CH. If I go from 13 to 78, that is 6 times the amount because I have 6 times as large for benzene. Then for methanol, CH2O, is the empirical formula. It has a molar mass of 30. For ethanoic acid, that's twice the amount of methanol. Its molar mass is 60. It's twice the amount, or twice the molar mass of the empirical formula. Glucose, if I said that the molar mass was 180, the empirical formula of glucose, they all have a common factor of 6. If I divide them all by 6, I get CH2O, which is methanol. Its molar mass is 30. That is 6 times as large. Right, and so that 6 gets multiplied times each empirical formula subscript. Right, so if I take 6 times CH2O, I will get C6H12O6, which is the empirical formula, or which is the molecular formula for glucose. And so I showed that down here, that how I go from empirical to molecular formulas and how it's multiplied by a certain ratio. In doing a specific example, what if I gave you percent composition data, or if I gave you data and I said, calculate the molecular formula of a compound whose molar mass is 60 grams per mole and the empirical formula is CH4N? Well, the first thing you do is get the molar mass of the empirical formula. And to figure out how many times I'm multiplying my empirical formula by to get my molecular formula, I solve for it by dividing molar mass of molecular over molar mass of empirical. And that's going to give me a whole number that I multiply by. So first, I was told that the empirical formula is CH4N. So I solve for its molar mass, that's 30 grams per mole, and there's all my work there. I get these numbers of 12, 1, and 14 from the periodic table. Those are the molar masses of the elements. It's 30. The molar mass of my compound is 60. We could clearly see that 60 is 2 times as large as 30, but if you couldn't see that, molar mass of the molecular over molar mass of the empirical, 60 over 30 is 2. And I take that 2 and I multiply it times my empirical formula. There's imaginary ones here by the C and the N, and we did that all in the first semester. So I multiply everything by 2, and this is my molecular formula. I'll do one last example, and then it's up to you to do the practice. So example 3, you'll see this in the near future. Percent composition of an unknown compound is as follows. It's 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen. And the molar mass of the molecular formula, that's later, is 116 grams per mole. The percent composition gives us the percent composition for the empirical formula. So I'm going to first start doing that. Remember, there are 3, and the question's asking what's the molecular formula. So remember on the page before, there are 4 steps. Assume that we have 100 grams of sample and convert the percentages to mass in grams. Convert the mass of each element to moles using the molar mass from the periodic table. Divide each mole value by the smallest number of moles calculated. Round to the nearest whole number. So I'll do that then. So I'm going to do carbon. I have 62.1 grams of carbon now. I have 13.8 grams of hydrogen and 24.1 grams of nitrogen, right? You convert the percentages to grams, and then you divide by the molar mass of each element. So I'm just going to do 12 grams per mole for carbon, divided by 1 gram per mole for hydrogen, divided by 14 grams per mole for nitrogen. These are the molar masses of carbon, hydrogen, and nitrogen, respectively. If I do this on a calculator, 62.1 divided by 12, I get 5.175 moles of carbon. If I do 13.8 divided by 1, I get 13.8 moles of hydrogen. If I do 24.1 divided by 14, I get 1.72 moles of nitrogen. And then I have to divide each of these by the smallest moles. That's the third step. The smallest moles given to me that I calculated is 1.72. So I divide each by 1.72. I already know this is 1 nitrogen. For hydrogen, 13.8 divided by 1.72, I get 8 hydrogen. And then 5.75 divided by 1.72, I get about 3 carbon, right? It said 3.3, but it's about 3 carbon. So now my empirical formula is this ratio of each of the elements in that compound, C3H8N. Its molar mass, by adding all of them, there are 3 carbons. The molar mass of this is 3 times 12 plus 8 times 1 plus 14. So 3 times 12 plus 8 plus 14. The molar mass of this is 58 grams per mole. The molar mass of my molecular formula is 116. Remember, I could get that N, which is my multiple. If I take my molar mass of my molecular formula, which is 116 grams per mole, and divide it by the molar mass of my empirical, this is about twice as much, so 2. So I'm going to take this and multiply it twice my empirical formula. So 2 times C3H8N, and I get C6H16N2. That is my molecular formula. I want you to use this information, and I want you to work on, if you have not already, the practice. there is a question on the front where it says propose a structure, C7H8, and you have to use EU and IHD and propose a structure that's consistent with that. And then on the back, I want you to do the same thing, where you get your percent composition and get the molecular formula, and then from that molecular formula, calculate elements of unsaturation and IHD and propose a structure. I'm going to do the front as an example of proposing a structure, so you could do the back on your own. C7H8, CnH2n plus 2 is my saturated hydrogens, how many I'm supposed to have. N in this case is 7, so C7H2 times 7 plus 2 is 16. I'm supposed to have 16 hydrogens. I only have 8. So subtract H8. I have 8 hydrogens that I lost. Or if I divide by 2, I have 4 H2s that I lost, which is the same as saying 4 elements of unsaturation. So now I have to have a structure that has 7 carbons and 8 hydrogens, and it has 4 EU. Well, I'm going to let you know as a little hint, if I see 4 EUs, I'll probably have this as the beginning of my structure. This is benzene. This is only 6 carbons. If I add one more, this is C7H8. Convince that to yourself. Another possible answer that I saw in class today was drawing 7 carbons, 1, 2, 3, 4, 5, 6, 7, and people were doing this, where they had like 2 double bonds next to each other. I guess that's possible, as long as you have the right number of hydrogens. I also saw this today in class. 1, 2, 3, 4, 5, 6, 7. And this is 2 double bonds and a triple bond. This is 4 EU. This is 4 EU. And this is also 4 EU. And prove to yourself that these all have 7 carbons and 8 hydrogens, because they do. These are all known as constitutional isomers. They're connected differently. They're all connected differently. Okay? Alrighty, so use this video to help you complete the rest of this practice and to understand how to calculate elements of unsaturation, how to calculate empirical and molecular formulas from percent composition, and then eventually propose structures.